morning. I want to talk to you guys today about hydrogen ion and the pH scale. All right, so a little background, acids versus bases. We've been reading about acids. They form hydrogen ions in water. They taste sour. They turn litmus paper red, and they are known as proton donors. Bases form hydroxide, that's OH minus, in water. They taste bitter. They feel oily, slippery, and soapy. They turn litmus paper blue, and they're known as proton acceptors. All right, so when you put a strong acid like HCl into solution, what happens, and you can see this over here on the left, is that hydrogen chloride will completely dissociate into its respective ions. So HCl dissociates into H+, and chloride ions into solution. A strong base like potassium hydroxide will also fully dissociate in a solution like water, and it will just dissociate into its respective ions, potassium and hydroxide. A question for you is pure water has a H+ concentration of 1.0 times 10 to the negative 7th molar, and a hydroxide concentration of 1 times 10 to the negative 7th molar. So I'm wondering what you think this means. I'd like for you to take a few seconds to think about that. So go ahead and pause the video and put some notes down, and then come back and we'll talk about it. All right, well, some of you may have been thinking about the fact that this number and this number is an extremely small number. So if you take that number and you put it into scientific notation, what you'll see is that's 1, 2, 3, 4, 5, 6, 7, an extremely small number of water molecules that are actually forming into H+ and OH- in a sample of water. Some of you may have been wondering, well, if this is pure water, why is it breaking up into hydrogen ions and hydroxide ions? Where exactly would the source of hydrogen ion and hydroxide ion be from in a sample of water? So a key point over here is that in pure water at 25 degrees Celsius, there's about 55.5 moles of H2O per liter. And so if you consider this, the fraction that is actually breaking up into hydrogen ion and into hydroxide is, once again, extremely small. But it is a process that happens, and it happens kind of automatically. And so we refer to this as autoionization of water. All right, and here's an image of that. So we have two water molecules autoionizing into H3O plus and OH minus. And so now what we're seeing here is that water does dissociate to a very small extent. And when it does, it forms hydroxide. And in actuality, the source of H+ is this species called hydronium. So it's not exactly H+, but it's this H3O+ that's formed. But the H3O+ is the source of H+ in solution. So I want you to take a look at this table over here, which is pH and H+ concentration. And I'd like for you to answer some of these questions, and then we'll come back and go over them. So the first question is, when the pH increases by 1 unit, how much does the H+ concentration change? The second question is, if you know the molarity of hydrochloric acid, how do you determine its pH? What's the pH of a 0.0 0.00001 molar HCl. And can you estimate the pH of a solution which is 0.0005 molar HCl? So take a few minutes to think about that, to look at this table, and then come back and we'll go over it. Okay, so first let's answer the first question. So as pH increases by 1 unit, you can see that over here, every time it does, so we'll compare these two here, what we notice is that the decimal moves over by 1 position. Okay, so what's happening is that the H plus concentration is actually decreasing by a power of 10 every single time the pH number goes up by 1. Okay, so we'll notice that the scale is kind of going in the opposite direction for acidity. So as you go up the scale and you become more acidic, the H plus concentration is the highest. And as you go further to the bottom of the scale, you can see that a really, really high pH is 14. You'll notice that you have the least amount of H plus concentration. And we use H plus as a determinant of the pH. Okay, so if you know the molarity of hydrochloric acid, how do you determine its pH? Well, let's just pick anything in here. Let's go ahead and pick this row. And we can see that here's the molarity. Once again, molarity, when we see it written like this, the capital M stands for moles per 1 liter. So in scientific notation, that gives us 1 times 10 to the negative 6 moles in 1 liter of water. Okay, and so what we're noticing is that the exponent is negative 6 molar. Again, a very, very, very small fraction of this solution has H plus in it. And what that gives you directly is the pH. The positive sign of that negative exponent gives you that pH number right there. Okay, so if we know that our hydrochloric acid is 1 times 10 to the negative 6 molar, then we know its pH is going to be equal to 6. All right, so the last one says estimate the pH of a 0.0005 molar HCl solution. So for this one, we don't have a coefficient of 1, we have a coefficient of 5, and our H plus concentration over here, what we're noticing is that these concentrations are always increasing by a power of 10. So what do we do in the case that our coefficient is a 5? Well, there's a handy little way to estimate that, but I think you can visually kind of already tell that if you're kind of halfway in between two different concentrations, in this particular case, you're in between, let's go ahead and see, this is 1, 2, 3, 4. So this is 5 times 10 to the negative 4. So if you're kind of halfway between the 10 to the negative 4 and the 10 to the negative 3, then you might be like 4 pH of 4 something, right? Maybe like 4.5 or something like that. But a nice way to estimate is that if you have a coefficient that's different than 1, like we do right now, this is a 5, what you can do is take the exponent, take the absolute value of the exponent, in our case that's 4, subtract 1, and that's going to give you a number, and then you're going to say that your pH is 3 point something. Okay, so that's a nice little way to estimate when your coefficient is not 1, but it's something else. Okay, so pH is related to hydrogen ion. We just saw that in that table. There's a nice relationship here that we just noticed, that pH is related to H plus because of this logarithmic scale. Okay, so pH is on a logarithmic scale, and so for that reason, we can use this equation to calculate our pH. If we know the H plus concentration, we're just going to plug into our calculator negative log and whatever that H plus concentration is. And then we can get our pH. All right. In contrast, if we're actually looking for the H plus and we have the pH, we can take the inverse log of the pH. So you can see that down here as written. So you can go ahead and write in your calculator 10 and then put an exponent, whatever the pH is. So let's say our pH is -3, and that's going to give us our H plus concentration, which is, in this particular case, 1 times 10 to the -3. Okay, so this looks very similar, this table over here, but it's actually different. This is hydrogen concentration and hydroxide concentration this time. So I'd like for you to study it. I want you to answer these questions. So the first one is, how does the hydrogen concentration change as the hydroxide concentration increases? I also want you to answer, how does the pH change as the hydroxide concentration increases? Next, if you know the hydroxide concentration, how can you determine the hydrogen ion concentration, and vice versa? Finally, what does the pH value tell you about the hydrogen ion concentration? And what about the hydroxide concentration? So go ahead and pause the video, think about these questions, and then come back, we'll go over it. All right, so let's look at the first one. It says, how does the hydrogen ion concentration change as the hydroxide concentration increases? So hydroxide is right here. And as we increase hydroxide, so increasing hydroxide is going down, because you can see those exponents, those negative exponents are getting smaller, which means that you're increasing hydroxide concentration. We'll notice that the H plus over here is actually getting smaller. Okay, so as the hydroxide concentration got bigger, the H plus concentration got smaller. All right, so how does the H plus concentration change? So as the H plus as the hydroxide concentration increases, so as hydroxide increases, the H plus concentration decreases. It's an opposite relationship, an inverse relationship. So how does the pH change as the OH concentration increases? So as we just went down and saw the hydroxide concentration increasing, what we can see over here in the pH is that the pH is increasing. So as the hydroxide increases, we have the pH increasing. If you know the hydroxide concentration, how can you determine the H plus concentration and vice versa? Well, let's take a look. So if we know, for example, that we have let's take a look at this row. If we have 1 times 10 to the -12th molar, okay, of our hydroxide concentration, that allows us to know the H plus concentration, okay, because there's a relationship there. If you take a look at the two columns, you'll notice that the exponents always add up to this number down here, okay, 1 times 10 to the -14th, okay? And so the relationship is that hydrogen ion times the hydroxide ion concentration is always going to be equal to a constant, which is 1 times 10 to the -14th. So if we know the hydroxide concentration, we can calculate the H plus, and likewise. All right, so what does the pH value tell you about the H plus concentration? And what about the hydroxide concentration? So what I hope we just saw together is that as the pH decreases, so here's a really small pH right here, as it decreases, our H plus over here increased. All right, and as the pH increases, our H plus decreases. Okay, so high pH is going to always equal low H plus concentration. And pH is always looking at H plus to determine what the pH value is. All right, so previously I showed you that the pH is equal to the negative log of the H plus concentration. But now another relationship that's also going to be true is that the pOH is equal to the negative log of the hydroxide concentration. So this is another way we can determine the OH concentration, is if we know the pOH. And so we have a relationship between pH and pOH, that both of these are always going to equal to the number 14. Okay, and that relates once again to our constant, which we just saw was 1 times 10 to the negative 14, is when you have the H plus concentration multiplied to the OH minus concentration. Okay, so we have a couple equations here. We've got the relationship that we just saw, the logarithmic relationship between H plus and OH minus. From that, we have a relationship between pH and pOH, which is equal to 14. And we also saw that pH and pOH are measured in a logarithmic scale, and therefore we can solve for the pOH and the pH as long as we know the H plus or the OH minus concentration. All right, so once again, this is like the key equation that you want to try to learn and practice so that you can easily determine some of the unknowns that we're interested in, whether it be pH, whether it be hydrogen ion, or whether it be hydroxide ion. Okay, so we started this conversation about water and pH. And so the question here says there is a pH associated with water. What does this indicate about the water? So remember, we started with the fact that pure water has 1 times 10 to the negative 7 molar H plus and OH minus. Okay, so interestingly, you can kind of see where this constant comes from, because if you plug in those values, 1 times 10 to the negative 7 times 1 times 10 to the negative 7, you'll see we get 1 times 10 to the negative 14th. And so this constant that we've been looking at is actually a constant that we get from water. And it shows, we call this the KW, which is basically just this constant, which is the how much basically water disassociates at 25 degrees Celsius. Okay, so this is just a little practice to finish. We have our equations up here that I just taught you, and we have a table where we're trying to figure out some unknowns with a few givens. Okay, so we'll start with this one right here. The pH is 3. And so we're interested to figure out what would the H plus concentration be if the pH is 3. So we learned that we can just go ahead and use this logarithmic relationship. If we know the pH, then the H plus concentration is going to be 10 to the power, the negative power of the pH. Okay, so that would be 1 times 10 to the negative third. Importantly, the unit is molarity. Okay, what would the pOH be then? Well, if I have 1 times 10 to the negative third, my unknown is the pOH, and that's going to be equal to 1 times 10 to the negative 14. Okay, then just going to end up dividing to cancel this from this side. Okay, when you have exponents dividing like that, they subtract, which negative and a negative, that's going to turn into a positive. All right, and so what I end up with is 1 times 10 to the negative 11th. Okay, so, whoops, that is actually going to go into my OH concentration. So this is 1 times 10 to the negative 11th. Okay, what about the pOH? So if I've got a pH of 3, I know that the pH plus the pOH is equal to 14. And so I'm going to put 3 there, plus x is equal to 14. So I'm going to go ahead and subtract 3, and my x is equal to 11. Okay, so is this acidic or basic? The way I determine that is I always look at the pH, very important. The pH determines the acidity or the basicness. And it is below a 7, and so far I'm going to put this as acidic. All right, so I'm going to let you fill in the rest of this table. Good luck with that. And with the key idea for today, the question was, how is the pH related to the acid-base concentration of a solution? So you should stop and just reflect on that question. You should come up with maybe at least 5 different things that you can now say, which is a relationship between pH and acid-base concentration in a solution. Take care, you guys.